So, as we said, Laplace transform is used in modeling and analyzing various continuous time systems. So, the previous discussion, what we are discussing is Laplace transform in periodic functions. So, we are working on periodic functions. You know, in Laplace transform, the main important idea where it is used as case study in various real-time problems are in analyzing continuous time systems wherever time is involved. For example, telecommunications you take, signals you take, it all depends on time domain. It is connected with time domain, right? It is connected with time domain. So, in time domain related areas, in whatever it is, it's connected with periodic functions. So, in modeling the structure, modeling the design, and understanding the what is the response it could give to the inputs involved inside, because you know, if you take a system and have multiple modules in it, so all there should be a transient response to every input given into it. Okay, so in that areas Laplace transform plays a very important role. Am I right? What is next? So like signal processing, what do you mean by signal processing? So whatever we talk, so you hear, no, it can be noisy, it can be streamlined, it can be turbulent, it can be anything. So if you want to process that signal, in processing the signal, if you want, suppose when he talks, it looks like so high pitched sound. Okay, if he talks in a high pitched sound, but it should be modulated. Like how you tune, no? I want to reduce this volume. I have to reduce this volume. So I am processing that signal. So and also there is a mix up. If something is getting some noise is mixed inside it. So filtering. So like in filtering areas and like in signal processing and analyzing the various signal systems, we can use Laplace transform as a tool to work with to get the outputs. Am I right? So what is next? What is next?
Laplace transform in circuit analysis.
So in circuit analysis, in circuits, you know, there are a lot of things involved, a lot of components, there are transistors there, capacitors there, condensers there, all of various types of components are there. So it makes a design, it makes a system. So in working into it, in circuit analysis, in analyzing those ideas, in picturizing what is the output, what can be the solution in such areas, we can even apply Laplace transform as a tool to understand what can be the outcome. Also, like not only this, Laplace transform as a case study, it is used in various areas. Like for example, you can take fluid flow, you can take mass transfer, you can take heat transfer. Okay, when a real-time problem is converted into, for example, as differential equations, when they are converted into differential equations. So differential equations can be solved. Complex differential equations, finding the solution for the differential equations. It can be of second order, third order differential equations. All these things can be taken as a case study, can be worked on using Laplace transform. Because Laplace transform is a user-friendly tool. Okay, it's user-friendly tool. Only thing is it has certain restrictions in it. So if the system can adapt to that kind of constraints, so we can work on it. So, like Fourier transform. Fourier transform is a very good tool when it comes to communication systems. Okay, in communication systems, a very important tool. Fourier transform. Similarly, Laplace transform has its own space. So it does. So you can see multiple areas. So modeling and analyzing continuous systems, because in signal processing there are two types of systems. One is discrete type of systems are there, and continuous types of systems are there. So for discrete systems, we usually work with the summation areas. But continuous systems, we will work with the integration. So also, you know, Laplace transform works with the integration. Okay, in integration, we work in Laplace transform to get the right solution for the continuous time domain related systems. There are even like this. We have Z transform. Z transform is useful in somewhere where discrete data systems are involved, because that Z transform is connected with summations, where we don't go with integration or differentiation, we work with summations. But when we talk about the integration, we work on Fourier transform and Laplace transform, because these two are very, very important, because in nature we talk more on continuous concepts. Okay, so that's why we took this area as case study. Thank you.